Welcome. This question says, show that a particle of monatomic ideal gas contains 2.1 times 10 to the minus 21 joules of energy at 100 degrees Kelvin, and it tells you that the Boltzmann's constant is 1.4 times 10 to the minus 23. So here's our particle. It's monatomic, meaning that it's like helium or neon. It's just a single atom, and we can regard it as a particle. So it's got X translation, and it has Y translation, and it has Z translation, but it doesn't have rotation, and it doesn't have vibration modes. So it turns out it has 3 degrees of freedom. Whereas if I had a gas like oxygen, for example, then that would have X translation, Y translation, and Z translation. These are independent motions. And then you could be rotating about your x-axis, you could be rotating about your y-axis, and you could be rotating about your z-axis. Now, in fairness, with the shape of the molecule being like a dumbbell, you can imagine one of those is lined up along the common axis of the 2 atoms, and so one of those actually goes to 0. It has no energy storage capabilities. But then you also have the possibility for having some vibration on this, and you can represent the vibration by a kinetic component and a potential component. So in principle, when you look at these things, you see that for a diatomic gas, for example, there are 3 translational modes. There's 3 but rotational, but in practice that goes to 2 rotational because one of them is 0, and you have 2 vibrational modes. So that's a possibility of, in reality, it's 7 modes of freedom. 7 degrees of freedom, if you like. Now, not going too far off subject, but it turns out only at high temperature do you get all 7 of those accessible. For a diatomic gas, under most room temperature circumstances, you would have something like 5 of them being accessible. And if you cool down the gas enough, you'd have only the 3 translational ones accessible. But because of the shape of the monatomic gas, there's only, the rotation makes no sense with a monatomic gas, and vibration makes no sense with a monatomic gas. It's just translation. So we have 3 degrees of freedom. And equipartition of energy says that basically our energy is equal to 1/2 kb, that's Boltzmann's constant, times the temperature per degree of freedom. And so because this has 3 degrees of freedom, the energy available, or the energy stored in an atom of this gas, would be 1/2 kb times T times 3, because we have 3 degrees of freedom. So our energy would equal 1/2, and then it would be 1.4 times 10 to the minus 23 times T, and T has to be in Kelvin, so in this case that would be nice, it's 100, and then we multiply that by 3 because of the 3 degrees of freedom. And this is for one particle, so we look at this and we go 0.5 times 1.4 second e to the minus 23 equals, I like to do it bit by bit, and then we have times 100 equals, and then times 3 equals And we end up with 2.1 times 10 to the minus 21. 2.1 times 10 to the minus 21 joules. And if we think about a joule being the amount of work required to lift an apple from the floor onto a table, and this is a lot less. This is a tiny amount. Now it's only one particle. Mathematically very simple. It's basically being comfortable with the conceptualization of monatomic means only 3 degrees of freedom, and then being able to work with recalling the equation and being able to work with it from there. So there we have it.